In this lecture we will explore the fate of stars that start with fairly large mass. As you can see in the picture above, if the core is up to 1.4 times the mass of the Sun to begin with, then the star will end up as a white dwarf, as we said in the last two lectures. Now what happens to stars towards the upper left of the HR diagram on the main sequence? According to this table, you will see that they will become neutron stars if the core is a little higher, and if it's above 3 solar masses for the core, they'll end up as a black hole. Now, of course, we will need to understand first what a neutron star means and how we see it and how we detect it, and also what a black hole is. That's the topic of our lecture, and it does involve some research that I conducted myself. As you could see in the first slide, the collapsing of an iron core of a star that's way over 3 times the mass of the Sun will not create a neutron star at all, but rather something else. Why? Because the same way we found that quantum pressure can stop the collapse for a white dwarf by the electrons not wanting to be in the same place as each other, that would happen with neutron stars if the core was over 2 solar masses. So, to begin with, stars that are more than 20 times the mass of the Sun, when they collapse, a core of more than 3 times the mass of the Sun will end up not as a neutron star, but as what we would call a black hole. Neutron stars are already pretty close to that limit, but what is that limit? My main field of research over the last 20 years, however, has been black holes rather than neutron stars. So let's try and tie black holes first with something called an escape velocity. The escape velocity from a black hole is larger than the speed of light, so nothing can escape a black hole. Therefore, black holes themselves don't shine. So let's try and explain first what's an escape velocity. Okay, something for you to do. Hurl something up into the air. Your cell phone, your pen. Come on. No one's looking. Well, if it was your cell phone, I hope you caught it. If you threw it very, very gently, it came back after it went up a little bit. Then if you threw it harder, it came closer to the ceiling. And so on, so forth. But it always came back, so it did not escape. If, however, you stepped outside and hurled it, Hulkman that you are, at 7 miles per hour, 7 miles per second. Okay, 7 miles per second, right? So that's way better than any picture we have. So 7 miles per second hurling your cell phone, and it would never ever come back. It would leave Earth, leave the solar system, leave the galaxy, and will keep on going and going and going and going, better than the Energizer Bunny. The escape velocity from Earth then is 7 miles per second. Well, what if Superwoman came and shrunk Earth to 1/4 of its size? What happened then is that everything will remain the same almost, except for the fact that gravity is harder, and escape velocity is gonna be now 14 miles per second. Okay, you quartered the size, you doubled the escape velocity. Now if you keep on squeezing Earth to about the size of 1 inch across, the escape velocity would be the speed of light. So if you squeeze Earth to 1 inch, Earth will become a black hole. Black hole anywhere are black. Space is black. Black means something that does not radiate light. So how can we see these things? Next. Here are 2 artists' renditions of what we think black hole surroundings look like. Both are a bit naive. The distortion in both pictures are very tiny. The real distortions are much greater, and the artist chose not to include them as so that the viewer would not be confused. We will soon enough see, though, that the source of the distortion exists, and why I said here that the distortion should have been much larger. Still, you may realize from these renditions that there is something shining here, and it's not a black hole. It's a disk of material that's swirling into the black hole, from which we can hear its final screams in the X-ray part of the spectrum, or its final signals that we can see, I guess, rather than screams. In this slide, I'll show you what we actually see. First, here's a picture of where you can find one such black hole. If you look at the summer triangle in the chart for the lab, you'll find the star Deneb, which is part of the Cygnus constellation, Cygnus the Swan, and in that picture here you can see where the black hole is. Click to see under that map pictures of two black holes. These are two images of black holes. Each one is a very boring picture because the only light you're getting is from one pixel in the middle. In one picture in the middle of one pixel in the middle of a digital camera that is up in the sky on the Chandra X-ray telescope. If the black body emission is maximizing an X-ray, it means that what you're seeing is a disk that is incredibly hot, tens of millions of degrees at least. In fact, the amount of light coming from the particular disk on the right, for example, is more than the light of a whole galaxy. Now, the light from those black hole candidates, from those disks near a black hole, is flickering like crazy. The actual output is doubling or even quadrupling in matters of hours in this picture, and when we actually look at Cygnus X1 in the previous picture, in a matter of milliseconds. Now, the fact that the light is flickering in such a random fashion is very interesting, but the fact that it's flickering can be tied together with what we just said about the size of neutron stars. Milliseconds meant a source that's 300 kilometers across, 186 miles across, right? Now, the black holes are even smaller than that. And by measuring the orbit of a star around Cygnus X1, we can tell that it's about all the way to 8 times the mass of our Sun. So the density itself is huge, and the size tells us that that region in the middle, there is a region in the middle from which even light cannot escape. Now, that means the laws of physics are going kabunk, meaning some things that we thought, like escape velocity or like how gravity works, are going to change. And indeed, the next slides will deal with that situation.